Hello. I'd like to talk with you about some of the basic properties of the definite integral. It's the integral because it's got this curly s, and it's definite because it has values a and b. The results of definite integrals are numbers. There's some pretty cool properties that you need to be familiar with in order to effectively integrate definitely. So let's just go through some of these basic properties. And I'm going to tell you what the properties are, and I'm going to do a little bit of reasoning on the other side of the board. Okay, so the first one here has us working with the integral from a to b of some constant value c. And what is that? That's c times b minus a. The integral of a constant function is that constant times the width of the interval. The reason being that if I have axes and I have a constant function and I'm interested in the window from a to b, well, the integral is the area under the curve, the net area under the curve. And so it's this right here. It's this rectangle with width b minus a and height c. So the area of that rectangle is c times b minus a. Okay. The next one is the integral from a to a of f of x dx. If I integrate from the same number to the same number, right? What do we have? Diddly squat. Reasoning for this verbally is f of x is a rate of change. We allowed no time to elapse. So, of course, there was no change. Pictorially speaking, I've got axes. I've got a function. My interval is from a to a. Okay? So if I partition the width of this interval into little rectangles and add it up with little rectangles, the width of every rectangle is 0. Okay? So when I add up the amount of area underneath the curve inside this interval, well, the width of the interval is 0, and so I get 0. Which means, really cool, that if I write down some big nasty formula, if I'm like the integral of e to the sine of x squared divided by some other nasty thing, but I'm integrating from 1 to 1, the answer is 0. Okay. The next one is if I have a sum of functions right here. So the integral from a to b of f of x plus g of x is equal to, I really like this one, the integral from a to b of f of x plus the integral from a to b of g of x. I'm suppressing my dx's verbally. Let's not forget to write them. The reasoning for this one being, I've got axes, I've got an interval of interest, I've got a function, and then I've got another function above it. Okay, so that one's g, and this one is f. The amount of area underneath that one plus the amount of area underneath that one is equal to what I would get if I were to write f plus g, which is I take the height of f plus the height of g. So it's going to be somewhere up here. So that function right there is f plus g. So because we're adding one area to another, it just gets to be like that. The next one is about what happens when I have adjacent intervals. Okay, so b is right here and b is right here. I'm integrating from a to b, some function, plus I'm integrating from b to c, of some function, I get to just go the integral from a to c of f of x dx. Reason being, I've got an interval from a to b and an interval from a to c, and if I draw a function above this, and I draw this area right here, and then I take this area right here, I can add up that one plus that one, or I could just do it all at once, and I get the same number. This next one here is a little more subtle, maybe. So I've got what we're thinking of as out of order. Bounds of integration for my function because I'm integrating from b to a of f of x. Like I'm integrating from like 2 to 0 of f of x. Well, what do? You pick up a minus sign and you get to flip them, right? Boop. So you can trade the bounds of integration and you pick up a minus sign. The reason for that is like, this is like time goes in reverse. So the amount of change that happens according to the rate of change f from b to a is, well, you just have to run time in reverse, but then the change happens according to a negative sign. So if like water was draining out of the bathtub from 0 to 2, then if you were to go from 2 to 0, then water's flowing into the bathtub out of the drain. And finally, this one right here, this one's the constant product integration rule, says that I can pull c outside of my integral. So the integral from a to b of c times f of x dx is equal to c times the integral from a to b of f of x dx. So this only works, this super only works if this c is constant. It does not work if c is not a constant. You can't just pull an x out of an integral. That doesn't work. But you can pull 5 out, or you can pull pi out, or you can pull any other thing that you know happens to be constant, you can pull outside of the integral. Boop. The reason being that if I take my axes and I'm integrating from a to b, and I've got a function, so that's f, and then I scale it by c so that it's always c times then the amount of area that I had down here gets scaled up by a factor of c when I consider that total area. Like, if you drive twice as fast for the same period of time, you'll go twice as far. That's exactly the thing. If you were to go twice as fast, c would be 2, and your rate would be twice its thing. You would have gone twice as far, so you pull that out, and that's how far you would have gone if you hadn't gone twice as fast. Okay, so those are some basic rules of the definite integral, and I hope that they serve you well as you work toward your goal of mastering definite integration. Thank you. Bye.